We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way.
So in module number 5, we are going to start open delta connection of three-phase transformer. And the objective is to become familiar with the open delta connection of transformer. So let's start lecture number 4 on open delta connection. Now, when a bank of three single phase transformer is connected in delta delta, so a bank of transformer, three single phase transformer is connected in delta delta, and it's supplying a balanced three phase supply. That means each and every phase in 120 degree apart in time. So this each single phase transformer is supplying 1/3 of the total load. Now suppose if any one of the three transformer gets damaged accidentally, what will happen? So still it will supply the load, but the level will reduced. So for accidental damaged, for scheduled maintenance, if from this delta delta connected three phase bank one transformer is removed, if one transformer is removed, then it will supply the load but at a reduced level. Okay, and this configuration means the connection after removing this delta delta connection, if we remove this transformer, so this DD configuration is known as open delta connection. This is also known as VV connection or V connection. Now this open delta system, instead of three single phase transformer, now there exist only two single phase transformer. So now the bank is consist of two single phase transformer, and it is supplying a three phase power to the load with a reduced voltage level. And this is the figure of VV connection or V connection, that is open delta connection. Now this transformer is removed, this transformer is removed. Okay, so this is the figure. Okay, now out of this three transformer used, phase A, B, C, transformer of phase C got damaged and had been removed, so that in this delta connection both the primary and secondary, the coils to be connected between terminal C1 and C2, capital C1 and C2 for primary and small for secondary, are absent. And if you note that the direction of current in the primary and its corresponding coil in the secondary is opposite. So the direction of current is opposite. That means if this is IB, IA, IC, so the direction will be here will be IA, IB and IC. Okay, now let the primary supply line to line voltage are VAB, VBC, VCA. We know this is from our basic concept, VAB, VBC and VCA. and these three line voltages form a balanced set which is 120 degree in time apart from each other. So if we consider arbitrarily phase sequence, let me consider the phase sequence is A, B, C. So this is my phase sequence for this discussion. And suppose we have taken VB, VAB as reference. So VAB will be this, VP angle 0, VBC will be 120 degree apart. So VBC will be VP angle minus 120 degree, and VCA will be plus 120 degree. We know from our basic concept. And here this VP is the magnitude of primary voltage. So VP is the magnitude of primary voltage. Now the primary voltage phasor diagram form a balanced supply which is 120 degree apart. If we draw, it will be like this. So one will be this, another one will be this, and one transformer is not there. So this is VBC, VAB, VCA. Okay, and this is A, this is B, this is C. So this is the primary voltage phasor diagram. A three-phase balanced voltage which is same in magnitude and displaced from each other by 120 degree. Okay. Now voltage induced in the healthy secondary coils are available between the output terminals AB, and CA. Between A, B and C, because BC is removed. So the voltage will be VAB in secondary side, VBC. Magnitude of these two secondary voltage are determined by the per phase turns ratio. That means from the basic principle, we can say VAB by V primary by secondary means we know V1 by V2 equals to same in magnitude, VCA by VC equals to ratio of the turns ratio, primary number of turns, primary turns per phase and secondary turns per phase. So turns ratio A we know from our basic concept. This Vs is here the magnitude of the secondary line voltage. Okay. Now remember that primary and secondary coil of the same phase are put on same limb and are linked by same mutual flux. Thus the primary and secondary voltage of the same phase coil do not have any phase angle difference between them. So we can say this VAB equals to VAB by turns ratio, that is VP by A equals to VS angle 0 degree. So there is no phase angle between primary and secondary because they are linking the same flux, because they are put on the same limb. Similarly, VCA equals to this. Okay, now if I simplify this, thus there is no winding between the terminal BC in the secondary coil. We have shown in the figure that C1, C2 is absent. It is not in the secondary side. There exists a potential difference between this B and C. So that is denoted by VBC. So what will be my VBC? VB minus VBC. C. Okay, so this doesn't exist, but there exists a potential difference between B and C. So this BC equals to VB minus VC. So you can write it down, VB minus VA minus VC plus VA. This VA if cancel each other, we will get this equation. Okay, so VBC equals to, if we take the minus sign common, it will be VA minus VB minus VC minus VA. So that means this is minus VAB and this is minus, and the VC minus VA is VCA, and this is my VAV. So prior to this there is a minus sign. So VBC equals to this. If we take the minus sign common, VAB plus VCA. Now if we put the magnitude and angle, so this VAB equals to VS angle 0 degree, VS angle plus 120 degree. So again we put the de Moivre's theorem. Okay, cos 0 degree plus J sin cos 120 plus J 120, and this will become this. VBC equals to, we are getting the value as this. Okay, so simplify again we put this. So ultimately VBC equals to VS minus 120 degree. Thus the voltage across the three secondary terminal, what we got? We got VAB equals to this, VS angle 0 degree reference, VBC equals to VS minus 120 degree, this, and VCA equals to VS plus 120 degree. Now this is the interesting. Okay, so that these three line voltages form a triad of three balanced voltage of equal magnitude and displaced from each other 120 degree. Thus with two transformer only it is possible to obtain a three-phase balance supply. So one transformer is absent, but if we look, it's still supplying a balanced three-phase supply. So there is no difficulty in supplying a three-phase, and this is the phasor diagram of the secondary side. Okay, so this is, so thus with two transformer only it is possible to obtain a three-phase balanced set of voltage in the secondary with no difficulty in supplying a three-phase load. Now suppose all the three transformer are healthy, or we can say with the absence of one of the three transformer, it may appear that one transformer is absent, so it will provide 2/3 of the total load. The bank will now able to deliver 2/3 of the total power. It would be delivered. This is, however, it is not the case. Now suppose all the three transformer healthy and total power delivered to the load is 60 kV. Okay, now what is the power carried by each transformer? 1/3, that is 20 kVA. Now one transformer is faulty, two are working, open delta mode. So how much it will deliver? 2/3, that is 40 kVA. But now it is not true, so we have to determine how much it is delivering. Okay, now for healthy delta, VL equals to this, IL equals to this. So what will be my power? √3 VL IL, √3 V phase, and for delta we know the relation between phase current and line current equals to √3 I phase So it is becoming 3 V phase I phase. So we can say write it down in terms of delta, sorry, line to line voltage is root 3 VLIL or 3 V phase I phase in terms of phase voltage. Okay. Now suppose with one transformer faulty, now it is forming open delta, but the voltage is still balanced. So VL equals to V phase. Since 3 phase load is getting balanced voltage, it will draw balanced 3 phase line current from the open delta secondary. Balance supply it is getting from the primary. So load drawing balanced 3 phase line current. So this is the figure of the secondary side. So balanced 3 phase load. So the secondary will draw balanced 3 phase line current. So IA, IB, IC are balanced, but what about their magnitude? Okay, so line current from the two healthy coils, line B and C, IB, IC. Since this is damage, so this is the TX transformer damage, the total load must be reduced. Otherwise, the two remaining transformers get overloaded and damaged. So this two line current IBIC should not be more than the rated current in the corresponding phase coil. Otherwise B and C will get damaged. So this is my IB equals to IL1 equals to IBA equals to I phase angle 0 degree, and IC equals to IL2 equals to IAC I phase minus 120 degree. Balance current it is drawing, I have just mentioned. So the third line IL3 equals to IA must be equal to the minus IB plus IC using KVL. So this is my IB outgoing current and this is my IC outgoing current. So this is minus IB plus IC. So we are applying KCL at node A. Okay. So this is my IA. So if we simplify this, IA will become I phase 120 degree. I have just put the value and I have simplified it. Okay. So this is my IA, IB and IC. Look, this is also forming a balanced three phase supply of same magnitude. All are I phase and displaced by 120 degree. So it is thus said to prevent overloading of the two remaining healthy coils, the line current cannot be more than that in the individual phase coil. That is IL equals to I phase for secondary line current. So what will be the power for open delta? It is root 3 VL IL. Now this IL will remain as I phase. This will be not root 3 I phase, what we have seen in case of delta connection. So it will only draw the line current. So phase current and line current will be same. So previously it was root 3 V phase I phase. Now previously it was 3 V phase I phase. Now it is becoming root 3 V phase I phase. So if we simplify this, it will become 0.577, 57.7%, not 2/3. That is not 66.6%. It will be 57.7%. Hence, when one out of the three transformer in delta band fails, it is still possible to supply three phase load, but with a reduced capacity of 57.7%, not 66.6%. Okay. So that means when one transformer in a healthy three phase delta connection gets damaged, then the open delta mode it is still possible to supply balanced three phase power, but it will be reduced to 57.7% of its original value. So what should be the utilization factor? So my utilization factor is 86.6%. Actual capacity koto? How much? It is root 3 V phase I phase. And the sum of total installed capacity of the two healthy transformer, first one is V phase I phase, second one is also V phase I phase. So arithmetic sum 2 V phase I phase, so it is root 3 by 2. So only 86.6% is the utilization factor. So that means full capacity of the two healthy transformer cannot be used in open delta. So instead of using 100%, the utilization factor only 86.6%. Okay. And what is the individual share of the two healthy transformer? So each transformer, it is V phase I phase, and total 3 phase VA supply is root 3 VA I phase. So again it is 57.7%. Okay, so thus each of the two healthy transformers share 57.7% of the total VA, not the 50% of the total VA. So this is also interesting. And these are the few application of open delta. So for it is used for new area where in future if the increase of load is required, then one transformer is inserted in the open delta connection and it will able to supply that maximum demand for future load. And if one transformer is removed, it will form open delta connection, and that is required for my schedule maintenance. Okay, so these are the applications. So by adding a third transformer, the total capacity of the system increased from 57.7 to 100%. So there is an increase of 52.3%. Okay, so these are the reference for further study. So another you can refer electrical machine by Purkait sir. So you can also go through this book. Okay, thank you.